Down there, life continues. The traffic is awful, stocks go on trading, and Star Trek is still showing.
Good morning, grade 9 learners. Welcome to today's natural sciences lesson. My name is Mr. Sianda Madala, and this lesson is proudly brought to you by the Gauteng Department of Education. Right, this is our last lesson for the term, right? So I hope we came rejuvenated and waiting to hear what the lesson entails, right? So we're still exploring planet Earth and beyond, and today's topic is about the birth, the life, and death of stars, and specifically under the subtopic, the life and death of stars. So now let's quickly look at the lesson objectives. Remember, our lesson objectives is what we need to achieve by the end of this lesson, right? So meaning by the end of this lesson, firstly, you should be able to explain that stars change in their appearance over billions of years. Not only that, you need to be able to also explain that stars that look blue are usually hotter and younger than stars that appear red. Also, you need to be able to explain that our sun is about halfway through its life cycle and it is a medium-sized yellow star with a lifespan of about 9 billion years. Then lastly, you need to show understanding of the death of stars. That's all that you need to do or understand or explain or know after this lesson, right? And all this information is found under the CAPS document on page 83. Moving on. Now let's look at what we have done in the previous grades and also the same grade that lays a foundation to today's lesson. So in grade 7, we talked about what? The periodic table. We introduced the periodic table of elements. When we were talking about different elements, saying that the periodic table has about 118 of them, right? But we said that there is more room for discovery that is not limited to that 118, right? And we mentioned elements such as oxygen, hydrogen, helium, carbon, and so on. Then later on in grade 8, we discussed atoms. We said that atoms are building blocks of matter, and atoms are made up of subatomic particles such as protons, which are positively charged, electrons, which are negatively charged, and also neutrons that are neutrally charged. And we talked about what? The relationship between the Earth and other planets in our solar system. We said that we have 8 planets in total, and also planet Earth is number 3 from the sun. Then later on in this grade, we talked about what? Compounds, right? Which are 2 or more different elements chemically bonded in a fixed ratio, and also gave examples of compounds such as carbon dioxide, water, and so on. Now, we also have a baseline activity, right? Which I would like you to write and test your knowledge so far. So let's read through the questions. Number 1 is saying, explain what stellar evolution is and why it is a finite process. So you can see that it's for 3 marks, so you didn't need to do a lot of explanation there. Number 2, it's saying, write down the definitions for the following terms, right? A, star, the B, and then B, stellar formation, and C, nebula, right? So because you have to explain in number 1, and also you have to define for 3 definitions in question 2. I'm going to give you 5 minutes for this activity. Then let's meet again after 5 minutes. Welcome back, grade 9s. Remember, if you have any questions or any comments regarding this lesson, WhatsApp us on our WhatsApp interactive number, which is 07957829008. Now, let's look at the solutions together, right? But before, let's repeat the question so that we understand what we should have written or what we have written, right? So number one is saying explain what stellar evolution is and why it is a finite process. Then number two, write down the definitions for the following terms, right? A star, stellar formation, and also nebula. So let's look at the solutions. For number one, right, explain what stellar evolution is. And stellar evolution is simply the birth, the life, and death of stars. It's simply what the life cycle of stars. And why is it a finite process? It is the process whereby a star will undergo a sequence of radical changes during its lifetime, and also depending on the mass of the star, this lifetime ranges from a few millions for the larger stars and also trillions of years for the smallest stars. So stars also need fuel for stellar evolution, but they only have a limited amount, so will run out. And this is why we say it is a finite process, or they have a finite existence, right? So now just quickly take a minute to copy down this statement as your corrections, then we'll move on to number two. All right, grade nines. Now let's move on to number two, right? So that we move on and sail together with the ship, right? So number two, we had to write down the definitions, right? A, it's the star. And a star is a massive luminous sphere of plasma held together by gravity far out in space, right? Then B, it's stellar formation, which is the process whereby dense regions within molecular clouds in interstellar space, known as nebulae, collapse into spheres of plasma to form stars. Then C, nebula. This is the giant interstellar cloud of gas and dust, and the fuels or gases of a nebula are mostly hydrogen and helium, as well as smaller amounts of carbon, nitrogen, and oxygen. So let's take another minute quickly to copy down the corrections, then we move on with the lesson. Welcome back again, grade nines. So now, since we have all the corrections, right, let's move on together with today's lesson. Remember, today we're focusing on what? On the life and death of stars, right? So now, the important terminology that has to do with this lesson. The first term that we have there is a star, right? So a star is simply a shiny point in the sky or in the night sky, and a ball of burning gas in the universe, right? Then we have stellar evolution, which is the birth, the life, and death of stars. We then have gravitational contraction, which is the process whereby a nebula's gravity overcomes its internal pressure, causing a collapse. We also have nuclear fusion, which is the process in which atoms combine to create larger atoms and massive amounts of energy. That's not only that, right? We also have what? Kelvin. Kelvin is the temperature scale used in science, right? So it's simply the unit used to measure temperature, and the symbol for Kelvin is K. We also have solar mass, and solar mass is the standard unit of mass in astronomy, equal to the mass of the sun. Then the last one is magnetic field, which is the region around the magnetic material or a moving electric charge where the force of magnetism acts. That's all for our terminology, right? So now, before we continue further with our lesson, right, let me just remind you how the star is born before it lives and dies, right? So now, we said that a star is a shiny point in the night sky or a ball of burning gas in the universe, right? And stars look like this, right? As we see in our picture, we have examples of this shiny point in the night sky, which we call what? Stars, right? So now, how are stars born, right? Remember, before, they exist for a finite period of time, right? Meaning what? They are born, they live, and also they die, right? So as we say that stellar evolution is the process by which a star undergoes a sequence of radical changes during its lifetime. So as it is born, it is the same as us human beings, right? You undergo certain changes in your lifetime. You are born, you become a toddler, from a toddler to teenager, an adult, and so on, right? And in that process, you're going through a lot of changes. So a star is almost the same, right? It is born, it lives and undergoes various changes, and also it dies, right? So now, before it dies, it depends on the mass of the star. So this lifetime ranges from a few millions for the longest stars and to trillions of years for the smallest stars. So now, I'm just reminding you of how a star is born. So remember, we said that a star is born in that collection of dust particles and what? And gas particles, right? Which we call a nebula, right? And now this is a NASA image of nebulae for plural or many nebulas, right? So now this is the NASA image of nebulae showing what? The birth of stars, that collection of dust and gas particles combining and also giving birth to a star, right? So now, it is also due to gravity and contraction, right? When the part of the nebula starts to shrink and collapse under the pull of its own gravity, forming the next phase of what? Of a star, which we call what? A protostar. So in that nebula, when it starts to shrink and collapse under the pull of its own gravity, we form the second phase, which what? Which is the protostar. Then from the protostar, when the protostar has existence now, is existent, right? What happened? What happens is that as the protostar begins to take shape during its gravitational contraction, it heats up, right? Large amounts of heat are released, and its gravitational potential energy is converted to kinetic energy of individual gas particles falling inward. So now, these gas particles and dust particles, they start to move and bounce what? All over each other, forming what? Or converting the energy into movement energy or kinetic energy, right? And they fall inward. So as they fall inward due to gravity and contraction, right? These particles, as I've said, they crash into one another, converting their kinetic energy now into thermal energy. So from those gas particles, when you have them clashing into one another or crashing into one another, as you can see in this diagram, right? There's a lot of movement. So that kinetic energy or movement energy is then converted into thermal energy, which is heat energy. And as the heat energy is produced, right, the temperatures will continue to rise until nuclear fusion begins to take place. So now, from nuclear fusion, that's where you start having what? This glowing star or the shiny point where in our sky or in our night sky. So stars shine as a result of nuclear fusion reactions deep within their interiors or cores, right? So here's an example of a star being born from that nebula, which is a collection of dust and gas particles, right? Forming a protostar, nuclear fusion taking place as the temperatures continue to rise and being enabling the what? The star to shine. This is because of the continuous nuclear fusion taking place where at the core or the interiors of stars. So now, as a star forms, the rate of nuclear fusion also increases. The more the nuclear fusion takes place, the more the star keeps on shining, right? So as a star forms, the rate of nuclear fusion increases until the amount of energy produced in the core is equal to the amount of energy radiating from the surface, right? And now, what happens to this energy? This outflow of energy from the core, it provides the pressure necessary to keep the star from collapsing under its own weight, right? So it's the pressure against what? Gravity. So that it keeps the star in position and it keeps the star glowing, right? So this outflow of energy provides enough pressure so that it is necessary to keep what? The star from collapsing under its own weight. Right, so now we have a star being born and it's shining, right? So pressure from inside the star, it finally equalizes the gravity pushing in and stops the star from contracting, as I've said now. So now, once the star has ignited, it becomes a main sequence star. So in this case, it is in its main sequence, right? As you can see here, these stars that we have in this picture, they are in their main sequence, right? They've ignited because of what? Of the nuclear fusion happening inside the cores of these stars, right? So now, in the main sequence stars, they start to fuse hydrogen to form helium, right? Releasing enormous amounts of energy. That is via nuclear fusion, right? When you have what? The fusion of 4 hydrogen atoms to form what? One huge helium atom. And it takes about 10 billion years to consume all the hydrogen in a main sequence star. So basically, it means that a star can last to up to 10 billions of years, right? Because of what? Of the enormous hydrogen that keeps on fusing with with another hydrogen to form with what? To form what? To form this helium. So now, we notice that as you look at stars, stars are of different colors, right? So now I want us to talk about the different colors of stars and what they mean, right? So now, usually, the fact is that stars that look blue are usually hotter and usually younger than stars that appear red in color. So when we say hotter, we mean in terms of temperature, right? They are usually hotter and younger than the ones that appear red in color, right? And the same goes for what? For the red stars, right? They are the opposite of the blue stars, right? They are usually what? Colder and older than the stars that appear blue, right? So now here is an example of a red star, and as you can see, these ones, they are all examples that are of stars that appear red in color, right? So what do these different colors mean, right? So now, however, the larger the mass of the star, the faster it will move through stellar evolution. So the larger the mass of the star, right, the faster it will be born, it will live, and it will die, right? Hence we say the faster it will move through stellar evolution. So we have a way of classifying stars according to their color, their temperature, and mass, right? As it reads here, it says, a way of classifying stars is according to their color or spectral class, as it gives an indication of their temperature. So bear in mind stars that appear blue in color, they are usually hotter and younger than the ones that appear red in color, right? So for example, a red dwarf is a small and relatively cool star during its main sequence. So now here we have a table that shows what different colors, a conventional color description, and actual apparent color that you and I see, right? And it has what effective temperature that the star ranges in and the class, right? So now let's go through this table together. We have class O, class B, class A, class F, G, K, M, L, T, Y, right? Those are the different classes which we can classify what these stars according to their temperatures, according to their colors as well. So when you look at O, right, the effective temperature there, right? But before we talk even about effective temperature, the color there is what? Is blue. And remember what we said about blue stars. They are usually hotter and younger than the ones that appear red in color, right? So the color that we see there is what? It's blue. And the effective temperature there ranges from what? From 30,000 Kelvin, right? It is having a blue conventional color, and the actual color that you and I see is also blue. But as you move now, right, you move with the class going to class B, you find the temperatures of the stars ranging from what? 10,000 to 30,000 Kelvin, right? And the conventional color description is blue white. But the color that you and I see is deep blue white. It is still hot, right? So now, at class A, now you find stars ranging at the temperature of what? 7,500 to 10,000 Kelvin, right? And these ones, they appear white in color, or the color that you and I see is blue-white, right? But their conventional color is white. Then when you go down with class F, you find the temperatures of stars ranging from 6,000 to 7,500 Kelvin, right? So now, the conventional color there that we find is yellow-white, and the actual color that we see, you and I, is white, right? But now, notice this one, and remember our topics from grade 8, right? Notice this one. Remember the temperature of the sun. At class G, you have what? 5,200 what? Kelvin to 6,000 Kelvin, and it has what? A yellow conventional color, right? And the color that you and I see is yellowish white. Are we together? So going down there, we can see that the temperatures, as you go down with the table, they drop, right? And as they drop, the color of the stars, they change, right? Having what? Red being there, one of the cool stars and old stars, right? So now, just to test ourselves in terms of how much we have learned so far, right? We have activity 1 here. So it says, why does a star not collapse under the weight of its own gravity when they are in their main sequence of their life, right? Then number 2, describe how stars are classified according to their color, mass, and surface temperature. That's what you need to do for your baseline activity. So let's meet again after 5 minutes after you have completed this activity. Welcome back again, grade 9s. Remember our WhatsApp interactive number 0795782908, right? Send in those answers or any comments or questions regarding this lesson. So now let's look at the solutions. Now, for number one, the rate of nuclear fusion increases until the amount of energy produced in the core is equals to the amount of energy radiating from the surface, right? And that's not only that. The outflow of this energy from the core provides enough outward pressure to keep the star from collapsing under its own weight, and pressure from inside the star finally equalizes the gravity pushing in and stops the star from contracting, right? So now, because this is a lot, take a quick minute to copy down number one, then we move on to number two. Welcome back again. Now let's look at number two quickly, so right? So number two says that stars that look blue are usually hotter and younger than the ones that appear red in color. And the larger the mass of the star, the faster it will move through stellar evolution, right? Meaning it will, the faster it will be born, it will live and die, right? So a red dwarf is a small and relatively cool star on the main sequence, and stars can be classified according to their color or spectral class, which gives an indication of their temperature. So let's quickly take another minute to copy it down and continue with our lesson. Welcome back again, grade 9s. Now remember, we're still waiting for those answers or any questions on our WhatsApp interactive number on the screen, right? So now, moving on. The sun is a star, right? Now we're dwelling more onto the life of a star, right? And we're making a reference from what? From the sun as the star. So we know that the sun is a medium-sized star, right? And the sun is made up of these gases such as hydrogen, helium, carbon, nitrogen, and oxygen, right? So the sun's energy spreads out into the solar system in the form of heat and light, right? So now, if you think of the star and its color, right? Now, it produces, it's what? It is a red dwarf, right? So now, looking at this, it produces heat and light. This is because of what? Of the new or the continuous what? Nuclear fusion taking place in the core of the star, where you have the hydrogen fusing with another hydrogen to form helium and enormous amounts of energy, right? So if you remember, we said that the star is made up of different parts such as the convection zone, radiative zone, inner core, photosphere, chromosphere, and corona, right? So those are all the parts that are in the sun as our star. And in the inner core there, that's where you find most of the nuclear fusion taking place continuously, burning what? And shining what? The sun. So now, since now we know that the star's life cycle has been covered, the details of the most important star's life can be revealed now, right? So can you guess what type of the star the sun is? And get to know that in the following slide, right? So now, the sun was born like any other star, out of a nebulae and into a protostar, right? Out of a group of what? Of gas particles and dust particles, right? Which is a nebula, right? And into a protostar, such as any other star. So it is now in its main sequence and can be classified as what? As a yellow dwarf, right? Because of its color, right? So the star is about 4.57 billions of years and about halfway through its life cycle. Why do we say so? We say that because of what? We say that the star is existent for what? For 9 billions of years. And now it's on its 4.57 billions of years. So it is halfway through its life cycle. So now the sun's death. Since the sun is considerably smaller, it will not explode into a supernova, right? This is why. This is because it is smaller in size, right? So it is not going to explode into a supernova, but instead, it is predicted that it will become a red giant in about what? 6 billion years. And when this occurs, all the waters on earth will be vaporized and life will cease to exist. And in the final phase, the sun will form a white dwarf and slowly fade out of existence. So now we are entering what? The death of stars. So now, there are one of two ways in which a star can die depending on its size, right? There are one of two ways a star can die depending on its size. Now listen to this. If the star is of low mass, right? If it is of low mass, it expands its outer layers, creating what? Nebulae, right? Creating nebulae, that collection of dust particles and gas particles, right? And a white dwarf forms from the core. But if the star is of high mass, right, death occurs in a massive explosion known as a supernova, and the remaining core then transforms into a neutron star or a black hole, right? So now, stars can die because of such reasons, right? Running out of fuel and contraction or contracting, right? So a star will eventually use up most of its hydrogen and fusion will slow down. Remember, the nuclear fusion is the one that keeps the star alight, right? It keeps the star ignited, right? Because of what? There's a lot of energy produced during that fusion, right? So now, as the hydrogen runs out, fusion will start to slow down. So the nuclear reaction stops inside the star, and because there is no longer any outward moving pressure from fusion to counteract the force of gravity, the star begins to collapse upon its own gravity, right? So this is when the star leaves the main sequence and starts to die, right? So also it can be because of brightening and swelling, right? So when the star runs out of readily available hydrogen, it starts to collapse. So the fusion of helium now begins in the core, forming what? Carbon and oxygen, right? Forming carbon and oxygen. Then the leftover hydrogen gas around the core continues to undergo nuclear fusion and forms an expanding cloud around the core. So this cloud causes the star to swell and form a red giant, right? And during this process, the red giant becomes about 1,000 to 10,000 times brighter, right? So what is a white dwarf? As we're talking about this, what is a white dwarf, right? Remember, white dwarfs, they form from the core of what? Dead red giants that were too small to fuse carbon. And since they do not undergo fusion, right, they have no energy source and gradually fade, right? So now when they radiate away all of their energy, they will theoretically become what? A black dwarf. So since white dwarfs cannot be older than the universe, no black dwarfs are currently in existence, right? So now here is an example of a white dwarf. Now, quickly, we have another activity, activity 2, right? It says, what is the sun made up of? And number 2 says, briefly explain what a red dwarf is, right? So I would like to give you 4 minutes to complete this activity. Then we'll meet again after 4 minutes. Welcome back, grade 9s. Now let's look at the solutions together. So what is the sun made up of, right? The sun is about three quarters of the sun's mass consists of hydrogen, while the rest is mostly helium, right? And the remaining 1.69% is made up of heavier elements including oxygen, carbon, neon, and iron. Then number two, briefly explain what a red dwarf is, right? A red dwarf is a small and relatively cool star on the main sequence, and they develop over hundreds of billions of years until their fuel is depleted. So let's just take a quick 2 minutes to copy down the corrections. Welcome back again. Now let's continue with our lesson, right? But now, before we continue, remember we're still waiting for those WhatsApp answers, your questions, or any comments regarding this lesson, right? So let me just give you a quick 3 minutes to answer, to ask any question, or to comment on this lesson. Welcome back, grade 9s. It seems like we do not have any WhatsApp messages, right? But now let's continue to summarize what we have learned for today. So today we're talking about the life and death of stars, right? So we said that once the star has ignited, it becomes a main sequence star, right? This is when once it has ignited. But now, before it ignites, let me just remind you again, right? A star is formed from that collection of dust particles and gas particles called what? The nebula. From the nebula, it forms what? A protostar, which will then be a star at a later stage due to what? To nuclear fusion. So now, once it has ignited, it becomes in its main sequence, right? So the main sequence stars, they fuse hydrogen to form helium, releasing enormous amounts of energy, right? This is due to what? Nuclear fusion taking place in the core or the center of the star, right? And also, it takes about 10 billions of years to consume all the hydrogen in a main sequence star. So meaning what? A star can last up until what? 10 billions of years, right? To finish up all the hydrogen in it and stopping what? Nuclear fusion from taking place. And we said that stars that look blue are usually hotter and usually younger than stars that appear red in color. So now we said that also there are one of two ways a star can die depending on its size, right? So now if the star is of low mass, it expands its outer layers, creating a nebulae, and a white dwarf forms from the core. But if it is of high mass, death occurs in a massive explosion known as the supernova explosion, right? And the remaining core then transforms into a neutron star or a black hole, right? So now, if you are done watching this lesson, just simply click on the complete and continue button, right? So that you can be able to close this lesson, right? So now, from me to you with much love, thank you and goodbye, and also good luck for your exams.